Thank you, Saeed. So I'm talking today about Quantinuum. We're the largest independent quantum computer company in the world. We have over 200 quantum PhDs on staff, and this growing company is a large portfolio of products created by our quantum computers. So today we're talking about quantum randomness from our security product called Quantum Origin. Just to put it in perspective, this is sort of where we fit in that quantum supply chain for security. First, you have quantum key distribution. Now, that requires specialized quantum networks. There's a bunch of people on the panel today that are going to be talking about that in a little bit. We also have quantum resistant algorithms as a part of this quantum supply chain. And those are like the NIST PQC algorithms that Saeed was just talking about. Now, they don't require a quantum computer to implement it or to create these algorithms. So it's a completely classical solution to some of the upcoming quantum threats around algorithms. But these algorithms don't cover anything about a randomness weakness. They don't cover anything about weak PKI keys. They're entirely focused on the algorithms. Now, that brings us to the third area here, this foundational provable randomness. That's what I'm going to cover today. And this is really about harnessing the power of the quantum computer to create provable randomness for the first time, and then being able to leverage that in classical environments to harden cryptographic keys and make stronger security up the whole stack, classical computers and classical networking. So let's do a little bit of a refresher on why randomness is so important. If you have weak randomness at the foundation, then you get predictable encryption. And that's really a bad thing. Because if encryption is predictable, then it's not providing any privacy or protection. Therefore, you don't have any security up the whole stack of solutions, from VPNs to cryptocurrency, zero trust network access. None of these security initiatives will actually have any protection or privacy if you have weak randomness. And as it turns out, detecting weak randomness is actually very difficult. For instance, these three attacks on weak randomness took about a decade each to finally discover them. Now, why? Why is because these attacks often happen in communications as they pass outside of your protected network or enclaves. So they don't show up in your logs. They're not protected by your firewalls, your filters, and even NIST 800-90B health checks, which are very good at detecting a complete lack of randomness. They're not able to prove that something is strong randomness because statistical analytics are unable to prove that in a classical environment and classical networks. So how do we solve this problem of weak randomness by using a quantum computer? First, we create a quantum seed by using our quantum computer and a series of Bell tests to create provable randomness. Now, I want to say it again, this is not possible with classical computers. So provable randomness is a new capability that quantum computers bring to the classical security world to help all of our existing cryptographic algorithms. So next, we package this quantum seed as a simple software install called Quantum Origin. And that can go to any classical operating systems such as Windows or Linux, or even RTOS systems like Zephyr. And ultimately, this software acts as a turbo boost to strengthen the local randomness by removing bias. And that protects against attacks on weak randomness, which we just saw on the last few slides. So let me say this again. Quantum Origin turbo boosts your system to protect against those attacks on weak randomness. So if you look at the right-hand side of this slide, you see that we convert any random number generator to a quantum random number generator just with a simple software install. And it's easy to install on servers and clients, even in the cloud and virtual machines. And there's no networking requirements. So this is applicable and it works in IoT environments like the energy sector. It works in military deployments. We've even deployed it to the International Space Station. And there's no special hardware requirements. So that just simplifies all the logistics of getting this extra level of security out of your randomness and your PKI stack. So next I want to drill into what does this really look like if you installed it on one of your machines in your network, okay? So first, we're pulling from your local randomness. And this can be any randomness available on your existing machines, such as RDC, CPU jitter, even a lava lamp. We really don't care what the randomness is. Even if it's weak randomness, we can significantly strengthen that randomness to protect against these types of attacks. In fact, we assume that your existing infrastructure has weak randomness because there's no way to prove how strong it is in classical computers and classical environments. And our software uses a randomness extractor powered by our quantum seed to remove bias and create provable randomness. And the result is really stronger randomness that protects against attacks on weak randomness. It's actually 10 to the 75 times stronger than NIST's full entropy. And that's the number 10 with 75 zeros after it. So it's really significant. And just a reminder, why is stronger randomness better? I bring us back to this slide that I covered a little bit earlier. But now, thanks to quantum computing, we have provably strong randomness as the foundation of our security stack. And this turbo-boosted randomness leads to hardened keys at the crypto level and delivers stronger security up the whole stack to your network security, authentication processes, and other systems that rely on cryptographic encryption for privacy. So overall, this is the power that we can bring with our Quantum Origin product. And that's all I had to present today. So thank you very much.